All right, so we're recording. Let's see here. Here's where we left off last time. So we're talking about how to draw pictures to represent multivariable functions. And it's, again, tempting to say, well, let's just use graphs. Aren't graphs easy and familiar? And wow, it just shows everything you could possibly want to know. It seems like the perfect way to represent a function with a picture. And the problem is if you have more than the very lowest number of variables involved in terms of both inputs and outputs. In any other than the most trivial of cases, you're going to have a picture that you can't draw, such as a four-dimensional picture. It's out of the question. It's a non-starter. Don't even try. And really, don't try. Right? It's make your brain melt. So graphs have this very severe problem that they have a very limited utility, except in the most trivial of cases. So we need to figure out other ways to draw pictures, but when you draw different kinds of pictures, of course, there's different ways to understand them geometrically. And what do geometric features tell you about the function algebraically? Right? So we talked about this one. Here's a totally different kind of picture. Totally different kind of picture. You could say that this isn't a very good picture because it doesn't really show very much of what the function is doing, and that's a fair criticism. But it is a picture. I can draw it. You got to give me that. Here's a picture of the domain. Here's a picture of the target, right? And there's some nice things that you can do with this kind of very different kind of a picture. And so when we see pictures like this, we're going to be, drawing certain things on these pictures, and you can't interpret what you see in these pictures as if they're graphs, right? If you see something that has a certain slope to it in this picture, that's not what the derivative is, right? So you have to make sure to keep the interpretations of the pictures separated by what kind of picture is it. So something to keep in mind. All right, so a new kind of picture we're going to talk about, an alternative to graphs. It's called a level set. And roughly speaking, a level set is what we call a pre-image. So let me first remind you what an image is. If you have an input point, you can look and see what comes out. That's called the image. When you put something in and you look and see what comes out, that thing that comes out, whatever that is called the image. A pre-image is just going the other way in some sense. A pre-image says, given an output, let's ask the question, what are all of the inputs that land on that output? That's the idea of a pre-image. Okay, so here's how you write that down algebraically. Again, what we call the level set. The pre-image is the collection of all points in the domain such that when you apply the function to those points, you get a fixed given output value. Now let's see some examples just so we can, relate practically speaking. So here is a multivariable function. 2 inputs, 1 output. And here's the formula for it. All right, so we've got a perfectly well-defined multivariable function here, and let's start looking at pre-images, aka level sets. Let's start with the value 1. Okay, the value 1. If I want to know what the pre-image, if I want to know what the level set is associated to this output value 1, going back up to the definition, I need to ask, a little bit further up. Whoa, wrong color. For this value 1, I need to know what are the input values that make the value of the function equal to that output value 1. So I am very literally going to just take that value 1, I'm going to set the function equal to this value 1. Following the definition. Is everybody on board? Now notice when I do that, that gives me an equation. Good news, in this case, it happens to be an equation that I recognize. Isn't that convenient? And that set, every point on this circle then, is a point whose image is the prescribed output value 1. And that makes this purple circle the pre-image. All of these points land exactly on 1. Is everybody on board? Okay, so you can do this with different output values. So for example, we can take 2. We can set 2 equal to the value of the function. That gives me, again, an equation. Now this is a different equation. It gives me a different curve. It's still a circle. That's nice. Different pre-image, different level set then for a different output value. Okay, so now altogether then, keep in mind my goal was not to understand particular output values. My goal was to understand the function itself. I'm trying to understand, I need a picture that helps me understand what this function is doing in some sense. And the picture that we associate then to that function is this right here. Notice it's entirely in the domain. Level sets all live in the domain. But if you draw enough of them, if you draw enough level sets, even though you don't get a perfect picture, right? Look at all the gaps in here, right? Just to quibble before we, I didn't draw anything in there. Great big huge gap. So I don't really know exactly what the function is doing exactly right there. Nevertheless, I kind of see somewhat of a picture, and I can draw some inferences from this. I can kind of get an idea of what my surface looks like here. Kinda. Now, before I go on and show you an example, I do want to address the complaint here of, look, I didn't draw anything in that little spot. I have no idea what's going on there. Doesn't that make this dramatically disappointing compared to graphs? I will point out that if you look back here to when we drew a graph of this function right here, it was an illusion when I suggested that what I drew here was a surface. Look at what I drew. There's a whole bunch of nothing in here, right? I'm using your imagination to convince yourself of a little fib that I have drawn an entire surface. I haven't, right? There's nothing in there either. So when you're drawing on a piece of paper, a graph of even a function of 2 variables also has this really bummer feature that there's a whole bunch of missing information there, right? So this is not really that big of a gripe against level sets, right? They both have big gaps. Of course they do. Okay. All right, so here's an example. Now, y'all may have seen things like this before. If you've ever done any hiking, you have what they call contour maps or topographical maps, right, that help you understand what the altitudes are, how steep things are as you're hiking along. By the way, you can get what they call contour maps on Google Maps, right? If you zoom in just the right level, and if you click one of the options, I think it's called I don't remember what they call it on Google Maps. But anyway, there's an option there. You look at maybe it's called contour map or something. But anyway, there's an option where you can see the contour lines, and you can get something that looks a lot like this. So if you think about it, contour lines are level sets. Specifically, they are level sets of the altitude function. Now, the altitude function, I think we've talked about before. It's a multivariable function, which for any given point on the map, right, gives us what is the altitude at that point. Right, multivariable function. Longitude and latitude are the inputs. Altitude is the output. Okay, so notice what a contour line is. The big idea of a contour line is that every point on this curve all has the same altitude. This curve has equation h of x comma y equals c, where c is whatever that value is that the function takes all of these points to, right? Keep in mind, that's the idea of a level set, is every point on the level set, they all have the same value of the function. that cool? Everybody happy? Okay. Yeah.
Are you meaning to have the function and the output have the same like h? Is that like something that you do?
Oh yeah, it's a pretty routine sloppiness. Yeah, technically it's a little bit inappropriate for me to use the same value, the same letter to represent the output variable as to represent the function itself, but people do it a lot. Yeah. Okay. All right. So, how would you use this picture? How does this help you understand the layout here? How would this help me make decisions about how I'm going to climb this mountain, for example? And I claim that this is a mountain because you can sort of see that all of these points here are at the same altitude, but then when you look at higher altitudes, it gets sort of smaller and smaller, and that's because you're looking at slices basically that are higher and higher up. So you can kind of sort of visualize a mountain here. Now, let's suppose that I were here and I wanted to get to the top of the mountain there. If you didn't know, right, if you just kind of, just looking at a map with no contour lines, you might think, oh, okay, let's just do that, right? And here's the thing, that's a really steep climb. That's rough, right? That's this might not even be possible. I don't know, but along in there, it's bonkers steep, and you can even kind of tell that from the picture because, after all, the amount of altitude that you gain between there and there, that's the same as the amount of altitude that you gain between there and there, right? So this is uphill. This is crazy, right? And it depends, of course, on the dimensions and the scale, and I don't want to get bogged down in that. But you can see certainly this is much steeper along in here. So I'll tell you what I would do if I were going to hike from that start to that end. I would probably do something kind of like that, right? And then notice I can see from the picture that my distance between contour lines, each of which is I don't know, whatever, 100 feet, whatever, right? There aren't any of them that are particularly short, right? I guess my shortest one would be along in here. And that's not that bad. Perhaps way more reasonable than trying to do that right there. Everybody happy? Okay. Unless you're just like, if you're an adrenaline junkie, then maybe that's what you want to do. But it's not for me. Okay. All right, everybody happy? Okay. So notice by looking at level sets, clumped together, collection of level sets, we can kind of visualize. We used level sets to analyze and make a decision off of this kind of a picture. And if we were to try to draw a graph, it would actually be significantly harder. For one thing, it'd be three-dimensional. I can't fold up a three-dimensional graph and carry it around in my backpack very easily, right? So much easier to have a two-dimensional map. Okay. All right. Now, neat fact. If you have a function of two variables, when you make a level set, and keep in mind, level set means you're setting the function equal to a constant, right? That's how you know that these are level curves, is f equals a constant. Check it out. That's the same thing as taking the graph. Now keep in mind, a graph is where you set the function equal to a new variable, right? Take that graph and then do a horizontal cross-section. Horizontal cross-section means consider the plane where height is a constant, so z is a constant. A horizontal cross-section of the graph means that I'm going to take the graph equation and the horizontal plane equation, combine them together, and all together you get f equals c. You get a level curve, aka a level set. So algebraically, it's just kind of the same thing. So visual demo. There you go. Multivariable function. Right, function of two variables. Same one we were looking at previously. Here's what the level sets look like as previously discussed. The level sets are circles, right? Again, level sets are where you set the function equal to a constant. Here's what the graph looks like. Keep in mind the graph is where you set the function equal to a new variable. So there's what the graph looks like. We've talked about this surface previously. We made an argument about rotations. That was last week, Will, of course. And that's this surface here. So we've got a picture of the level sets. We've got a picture of the graph. And sure enough, when you take planes z equals c, right, for various values of c, those cross sections, as they should be, are circles, just like the level sets. Everybody on board? Yeah.
Could you identify if the graph is concave up or concave down?
From the level sets? That's one of the shortcomings of level sets, is that that doesn't really come through very well in just because we have so arguably, for example, if this were a topographical map, maybe it's a mountain, maybe it's the inside of a volcano, maybe it's like a depression. That's a problem. It's just a weakness of the picture. Yep. Yes.
Do we just use like two different colors to signify going up or going down?
There's various different things you can try to do. Yeah, totally. Yeah, use like the spectrum as an ordering of colors. Yeah, that could be a helpful thing. Absolutely. Yep. All right. Okay. So moving along. Let's see here. So we've talked about graphs, we've talked about level sets, we've talked about parameterizations of lines and curves. They're all different pictures. So given a function, we now have several different pictures that we can draw to represent it. And now let me say that backwards. Given a picture, there are several different functions that picture might represent depending on which kind of a picture it is, right? And so it's important to keep this stuff in mind. So, for example, let's suppose I'm interested in this line for whatever reason, and maybe I want to know something specific about this line that will require the use of calculus. If I'm going to use calculus, I need to know what function this represents. Here's the landmine. When you're trying to ask what function this represents, you have to be explicit and clear in your mind. Wait a minute. Represents which function in which way? Do I want a function whose graph is this line? Do I want a function for which a level set is this line? Do I want a function that parameterizes this line? They're all different functions, because graphs, level sets, and parameterizations are all different constructions that relate algebra to geometry. Right? So, for example, it's not hard to persuade yourself that this function right here is a function for which the graph is our line. I'll show you how we know this. Because if I were to form the graph of this function, the way you form a graph is you take the value of the function, you set it equal to a new variable. I'm going to use y because the input was just x. So you set the value of the function equal to a new variable, and notice that this equation here is exactly equivalent to this equation right here. I just kind of moved some things around. They're exactly equivalent equations. Everybody on board? So this plane, whose equation I was given, that plane is the graph of that function. Everybody on board? Now, real quick, if you want to know how would I identify this function, I kind of pulled a fast one here, and I just wrote down the function, pulled it out of thin air, and then justified after the fact that this is the right function. How would you identify it? Notice that all I really had to do, once I made the observation that this equation and this equation are the same equation, the thing that characterizes this as a graph is the fact that some function is equal to y. Let me say that differently. What characterizes this as a graph is that I've solved for one of the variables. I've solved for y, right? So really that's all you have to do to identify what function you're looking at a graph of, is just solve for y. Anyway, it's just kind of a nice way to think about that process. Okay, same line now. Let's talk about this same line. Is this line a level set of something? And how would I identify what function is it for which this is a level set? This is actually a much easier question. I don't even have to solve for anything. I can see right here in the existing algebra, I'm looking at a level set. See? It's already stuff equals constant, right? The idea, how do you take a level set of a function, is you take that function, you set it equal to a constant. That's already in this form. So this line is a level set of that function. Notice it's a function with 2 input variables, not 1. Does that make sense to everybody? So the big thing to make sure you understand is that, eventually we're going to be doing what I call the calculus of graphs, or the calculus of level sets, the calculus of parameterizations. We've actually already seen some calculus of parameterizations, right? If you have a parameterization, the derivative of the parameterization is the velocity, right? So that's a geometric interpretation of the algebraic act of taking a derivative. So if what you want to know about your picture is what's the velocity of that curve, you need this function. You need a function for which the curve is parameterized by that function. And this function, totally different functions that aren't about parameters. Parameterizations don't have anything to do with those two functions. The derivatives of these functions up here have nothing to do with a velocity of that line. Does that make sense to everybody? Yeah, you had a question.
So where does the 6 go in the level set, or does it not?
Oh, that's just telling you which level set it is. So this is the function for which one of the level sets is the line. Here's the thing. This function has lots of level sets, right? So the 6 is telling you which level set, right? And there's a bunch more level sets. The level sets of this function are like this. It's got a lot of level sets. But the line is one of the level sets of that function. Is that cool? Yeah. All right, yes?
For the parameterization, can the 6 go on either the x or y component?
Can the what now?
Like the 6, does it go with the x or the y component? Does it matter?
I guess I don't know what you mean. So the parameterization of the line is this right here? So I'm not sure what 6 you're talking about?
Like the 2 minus 2t.
You're wondering where this 2 came from? Yeah. Yeah, so let me just remind you as well. So this is any given curve, such as, let's say, this line right here. There's actually a lot of parameterizations. So I think the answer to your question is yes. That there's a bunch of different ways that you could parameterize. I guess what I did here is I took this point and that velocity vector. Right? But you could have just as legitimately picked, this point and that velocity vector. Perfectly fine. Or you could, if you're feeling, weird, you could take this point and that velocity vector. Lots of options. Yeah, totally. Right. All right. So, going forward, and this is going to be very regularly experienced landmine concern that you're going to have to worry about, is that if you want to take a picture and understand it with a function, you got to ask which function. And the way you decide which function is to be clear in your mind. Well, do I want to interpret this as a graph? Do I want to interpret the curve as a level set? Do I want to interpret the curve as a parameterized curve? Which of the calculuses do I want to be able to take advantage of? That'll tell you which kind of a curve, which kind of a construction you have to interpret it as, and that'll help you understand which of these functions is the right function to be doing calculus with. Yeah.
Can you please explain like how the first graph has going from a set of real numbers like in the first dimension to the first one?
Yeah.
Explain how that can help us.
Oh, yeah. And this is something that you definitely have to keep track of. Now, just a reminder, this is the equation of the graph, right? It's a graph because, again, we've set, the value of a function equal to the output value of the function equal to a new variable. So now let's look at this function here. Notice there's only one input variable, right? Y is not an input. Only X is the input, and that's why there's just only X as the input. That means that my domain has only one variable. Does that make sense? But on the other hand, now let's look at this other function over here. Let's look at this function. This is what the function is, whose level set is my line. This function has two input variables. So it's a function of X and Y, and thus the domain is in R2. Does that make sense? Yeah. Right. Okay, so all of this comment stuff here is stuff I've already kind of talked through. Calculus is different for these different constructions. The calculus of level sets is very different from the calculus of graphs. And so if you're not crisp in your mind of what kind of a picture am I looking at, how am I interpreting this picture, if you just kind of blur and blend together all these interpretations, then you're going to get a lot of wrong answers. And that's a nasty, nasty problem. Okay, so heads up. All right. Neat fact. Sometimes you'll find yourself looking at a graph. Surface comes to you as a graph. And yet you're going to find yourself wishing, oh man, I really wish I could use the calculus of level sets on this thing. The thing I need to know is just right there in the calculus of level sets. But what I was given isn't a level set. What I was given is a graph. It's given as a graph. I'm currently interpreting as a graph. I can only use the calculus of graphs. How can I use the calculus of level sets? And the answer is this wonderful little result right here. It turns out every graph is a level set. And now to be clear though, a level set of a different function. So here's the idea. Suppose I'm looking at a graph. This is what a graph looks like. Again, you know it's a graph because we've got y equals. Makes it a graph. Is that cool? Everybody happy with that? Now, what is it a graph of? Well, it's a graph of this function right here, the thing I've set equal to that new variable y. Okay, so we've got a graph. Fine. Now, here's the trick. Not much of a trick. I moved one term over to the other side of the equation. Hardly anything happened. Right? In terms of the algebra there, it's trivial. Easy move. And yet, now look at my result down here. My result, this is a level set. I know it's a level set because I've got some function set equal to a constant. That's what level sets are. Everybody with me? But we have to recognize, really importantly, this function right here, f, that is not the function that we have set equal to a constant. That's just not what this equation says. This equation says this business is what I'm setting equal to a constant, not f. It's y minus f. Very different thing. Everybody see the little subtlety there? Okay. So this graph, let's see here. I'm kind of mixing my colors around. This graph is a level set. It's just that it's a level set of this new function called g that's computed by this formula, not a level set of the original function f. And now let's pay attention to variable counts here. How many input variables? What domain are we dealing with here? For example, my original function had n input variables, and so my original function was a function on Rn. My new function, the function whose level set gives me that graph, is a function that has Well, all of those same original in variables and a new one called y. You can see it right there in the formula, right? It has, therefore, n plus 1 input variables. It is a function on R n plus 1. So these are importantly different functions. They're defined in different places. They relate to the surface. And keep in mind, this is all the same surface. It's all the same, set. Whatever that thing is, this is, these are really morally identical equations. They relate to, this surface relates to these two different functions, though, in these importantly different ways. Okay. Everybody happy? Example. Suppose I'm interested in this graph. The question is stated, let's suppose, as, hey, let's study the graph of f. And the question you find yourself wanting to deal with is something that where the calculus of level sets is going to be useful. I know we don't know any calculus of level sets yet. We will pretty soon. But if the calculus of level sets is what I need, this is not at all helpful because I'm not looking at a level set of that function. I am looking at a level set of this function, and I can apply the calculus of level sets to that g function. And make very, very clear to distinguish in your mind, very importantly different, x squared plus y squared, very, very much not the same as z minus x squared minus y squared. Those are different. Okay. All right. So every graph is a level set, super nice. Sadly, it doesn't go the other way. Not every level set is a graph. Easy counterexample. Here's a level set. I know it's a level set. And it's easy to draw a picture of that level set. There it is. And it's not a graph, because if it were a graph, it would have to pass the vertical line test, which it clearly doesn't. Is everybody happy? So this is a one-way street, unfortunately. You can convert graphs to level sets, not vice versa. Okay, now the next several pages in the, of course I'm in the Chapter 2, Math219 notes. We've already done these next several pages. And we're going to move along now to the next section, which is about partial derivatives. A little preliminary note, just an FYI. In single variable calculus, you talk about the derivative because there's just the one, right? Sadly, in multivariable calculus, there's a bunch of different kinds of derivatives that make sense in different contexts and looking at different pictures and play different roles, and oh gosh, there's a lot to say about it, right? So we're going to be spending a week or so, I forget exactly, but a fair amount of time talking about derivatives and the various different kinds of them. So why do we use the same word, derivative, to refer to a bunch of different things? And, of course, this is not a super rare circumstance where we use one word to refer to different things. All it means is that these things have a common feature, right? They're all unified by something. And here's what unifies all the different kinds of derivatives we're going to talk about in this course. They all relate input changes to output changes in some way. They're all about, and they're depending on the circumstances, there's some relationship between input change and output change. So this is what I want you all to be on the lookout for. Every kind of derivative we talk about, you should be asking yourself the question, how, in what way does this thing relate input changes to output changes? Okay. All right. So that's a little foreshadowing. Let's dive into some specifics. We're going to talk about the partial derivative. Some of y'all who may have seen a little bit of multivariable calculus in the past may have seen partial derivatives. There's some really nice things about partial derivatives. I am a fan, despite what I'm about to say. I am a fan of partial derivatives, but I do think that they are overappreciated. So why do we start with partial derivatives? Well, roughly speaking, it's because it's easy. They're really easy to compute. They're really easy to relate to our existing knowledge of single variable calculus. It's just a very convenient little first step. It's also easy, sort of in terms of course structure, because the book starts with partial derivatives, and it's a pretty big deviation to reorder. If I were to do partial derivatives later, as I kind of in an ideal world would prefer to, that would create some significant logistical problems that it's just not worth it. And by the way, most books do. Most books start with partial derivatives because they're easy to compute and they're easy to sort of, understand as a first time thing. So I'm going to go ahead and follow along. We're going to do partial derivatives first, but I do want to give you all a warning. I think it's important to recognize that these are not the best way to think about derivatives ultimately. So yeah, we're going to do partial derivatives first. It's going to be your earliest experience, but don't let it be your foundational experience. Don't hang your hat. Don't set it in your mind that, okay, fundamentally derivatives are partial derivatives. No, that's really not the best way to think about derivatives. So that's just a heads up. So here's how we do it. How to compute partial derivatives. It's pretty simple-minded, really. Cheap trick, even. Here's what we do. We take our multivariable function. We have several input variables. That's the problem. We don't know how to take a derivative of a function that has a bunch of input variables. We only know how to do a derivative if there's just the one input variable. So the hacky idea, I'm going to say, is we got a bunch of variables. Let's just pretend that they're mostly constants. Let's pretend that all of them are constant except for just one of them. And, well, then if you've got a bunch of variables but they're not allowed to change, are they really variables anymore? They're not really variables anymore. Now they're just constants in your equation, right? And so effectively, by playing make-believe and pretending that all your variables are constant except for one, you turn your multivariable function into a single variable function, and then you can just take the derivative the usual way, this regular old derivative. Now, this is, I want to call made-up nonsense at this point, right? I just did it because I found it convenient. That does not mean that this is a useful concept. This concept, as I've written it down here, has yet to prove itself. Right? This could be, again, think back to, me in the second grade or whatever, 4 times 7. Shouldn't that be 47? Wouldn't that make life easy? Right? No, that's a useless concept. Likewise, this has yet to prove itself. So I owe you satisfaction on that. So now real quick though, here's the notation. We kind of steal the Leibniz notation. Whatever the one variable is that I leave as a variable, you use that as the variable in the sort of the denominator of the Leibniz notation in the kind of the usual way. Now the other important note is that these over here are not D's, right? These are a brand new symbol. Very importantly, not a D. D would mean single variable derivative. You can't take a single variable derivative of a not single variable function, right? So we have to use this other little symbol, otherwise it doesn't make any sense. And that's a real problem. And again, I emphasize, this is not optional, right? If you use D's in place of this new symbol, this partial derivative symbol, it's wrong. Got to make sure to use the right notation. Also important to recognize, some people seem to have been mistakenly under the impression that this is the lowercase Greek letter delta. It is not, right? It is delta kind of flops back over to the right at the top. This doesn't. So I'll tell you what I did when I first encountered this symbol, and I know this is seemingly ridiculous, but I spent about 5 minutes practicing how I was going to make it. Like I was in the second grade again, learning my alphabet. Right? Again, it's undignified and silly, but I think it's very helpful. You got to decide if you're going to sort of swirl outward or if you're going to swirl inward. There's two kinds of people in the world. right? So I have no position on that question. Do whatever you want. But anyway, think it through. Make sure that you can write that partial symbol comfortably. Okay. Alrighty. Now there's another notation that you can use in the same way that this is kind of like Leibniz notation of single variable derivatives. This is kind of vaguely like the Newtonian prime notation, kinda, in a way. The only big difference is there's a bunch of different variables again that I could hold constant, that I could not hold constant. So you have to indicate. You can't just say f prime. That doesn't tell you what is the variable that you're treating as a variable. So we use a subscript instead of a prime. But it's, again, fairly similar to the Newton notation. Is everybody with me? All right, let's see some examples. First, just a kind of a generic example. Now, this looks like a hard one. I'm going to take a derivative of sorts of this great big monster. It's a product of three factors, one of which is a cotangent. I hate those. And furthermore, the cotangent is a composition with a product. Oh my gosh, there's a lot of confusion and potential for this to get ugly, so it seems. Here's the beautiful point, though. Keep in mind, we are taking a partial derivative with respect to y. So y is our variable. That means that this factor right here, y squared, that's the only part of this function that is not a constant. Right? So keep in mind, all the other variables, x and z, you hold constant. If x is a constant, then e to the x, also constant. Which means, and also if z is constant, then e to the z is constant, and x squared is constant, and that product is constant, and this cotangent all just constant. It's a big, ugly, nasty constant, but it's a constant. And constants are awesome, right? If you have constants, multiplicative constant factors in your expression, as you're taking a derivative, and keep in mind, now that we've declared these constants, we're just doing a plain old single variable derivative of this expression. And the y derivative of y squared, nothing to it. The y derivative of y squared is 2y. And then the constants come along for the ride, as they always do, right? Nothing happens to them. They're constants. Satisfying? That's kind of beautiful. I propose, by the way, this as a nice example, that partial derivatives are not only reasonably easy to compute, I propose they are even easier to compute than single variable derivatives. Because with partial derivatives, you get to just declare huge chunks of your function to be constant and kind of ignore them in some sense. You don't get to do that in single variable derivatives, right? So, world's easiest derivatives to compute. Case could be made. Everybody happy? All right. But again, I also remind you that the young Bray product 4 times 7 equals 47, also easy to compute. So I hope you're not too persuaded by this, right? The fact that it's easy to compute. Okay, no, you're going to have to come to me with something like, how does this relate to geometry? How does this relate to something physical, perhaps? I need it to connect to an idea that I can make use of it with. Otherwise, I'm just playing really easy but meaningless games. Does everybody see the concern? Yeah. Okay. All right, so a couple more examples real quick. So let's suppose I want to take the x partial of this big expression, and there is an x there. That means all of this here I have to treat as a function, and okay, well, yeah, but good news. Y is a constant because it's not x. That means that this whole exponent, constant. And so while this might at a glance look like a really hard thing to take a derivative of, it's a function to the power of a function, oh my gosh, faint memories of logarithmic differentiation from high school calculus class. Nope. This is just a power rule deal. And the power, comes down and you subtract 1 and then don't forget the chain rule. Right? So this is actually a really easy derivative to take, as it turns out. Everybody see that? Almost seems too good to be true. Okay, let's do another one. Let's take the z partial of this expression right here. There's a z, but keep in mind, not being z, x and y are constant. That means all of this is constant. So again, now at a glance, it looks like function to the power of a function, but it's not. This is constant to the power of z. This is a function whose derivative gets explicitly addressed in single variable calculus classes, and it's just, the derivative of an exponential is that exponential times the log of the base. Right? Old fact from Calc 1. Everybody remember that? Okay. All right. World's easiest derivatives. Okay, so what does it mean? Is this just a bunch of nonsense? How do we interpret this geometrically? Is what I want to address now. So, okay, well, again, don't forget, you got to keep track of what kind of a picture you're looking at. The calculus of graphs, the calculus of level sets, very different. In this case, the way partial derivatives look on a graph picture and the way partial derivatives look on a level set picture, very different. And you cannot make a graph interpretation on a level set. So, again, very important to keep in mind what kind of a picture you're looking at. So, okay, we're going to start with graphs. Now, just to be explicit, I know this is a graph because look at the algebra I'm looking at here, right? The way that I've set this story up is that this surface, being a graph, z is my output variable. I've set the function equal to z. That's what makes this a graph. Okay, so we're doing graphs here. And that said, this function whose graph I'm looking at, so this function f, whose graph I'm looking at, that's a function, and I want to ask, what does the y partial look like on this picture? What in this picture geometrically is representing that y partial? So, good news. Our process of computing partial derivatives on the previous page, each step in that process, we already have an existing geometric interpretation. So here we go. By the way, we're going to be interested in computing this partial at the point a comma b. Keep in mind a comma b is the point in the domain where we're starting at. Keep in mind the domain is not all of this. Right, the domain is just the xy plane, which I'm going to be sloppy and interpret as being just the xy plane inside of the xyz space. Of course, that's a convenient way to think about it, but of course it's actually a separate world. But anyway, so this point a comma b is a point in the domain, and don't forget that the point up here, that's not a point in the domain. That's a point on the graph. That's a point that has 3 coordinates, not 2. Right? So I'm going to make sure to distinguish these from each other. Okay. So yeah, let's think about our existing interpretations. So again, we're looking at this point. Keep that in orange. Looking at this point. Step 1 in our process. We're taking a partial with respect to y. We have to fix all the other variables. Okay, wait a minute. What are my other variables? We're taking a partial with respect to y. That means I need to fix x. X is my only other variable. What does it look like geometrically when I fix x? And let me do this again in gray. Fixing x Well, here's the x-axis. Fixing a constant value of x. Well, I'm at the point a comma b. So if I'm going to fix x, it better be at the value that I'm at. And so I'm going to need x equal to a, which is that plane right there. Everybody on board? So now let me remind you, in this process of computing partial derivatives, step one, which I described algebraically here, we now have a geometric interpretation in the context of graphs. In the context of graphs, what that looks like is take this cross section perpendicular to the x-axis, or you might say cross section in the direction of the y-axis. Now this is a constant little source of confusion. You got to keep track of, wait a minute, which variable am I setting equal to a constant? Which variable, therefore, is the variable that I see in the equation is x. But because of the way that geometry works out, that means that the plane itself is parallel to the y-axis. So heads up on this little landmine. Just make sure to keep it straight. How you choose to keep that straight is very much up to you, of course. But make sure to keep that straight. Okay, is everybody happy? Okay, so we fix all the other variables. So in other words, we're looking at this cross section. When you take a cross section of a surface, here's our original surface. When you take a cross section, that just gives you a curve. If you think about it, that's a curve where the height is representing the value of the function as your variable, y, the only remaining variable, changes. So we have height as a function of input variable. In fact, this purple curve is a graph of our brand new single variable function, right? The green surface is a graph of the original function of two variables. This purple curve is a graph of my new single variable function. And with that in mind, what's our next step? Our next step is to take the derivative I better do this in blue. Take the derivative with respect to y of this function. So we're going to take the derivative, with respect to its input. What's a derivative? Again, old news. A derivative of a single variable function, when you're looking at a graph, which we are, derivative just means slope of the tangent line. So that's your interpretation. This is the geometric meaning of a partial derivative. A partial derivative with respect to y is the slope of the tangent line. And already, before I even finish that sentence, you're probably feeling a sense of comfort and familiarity. Slope of the tangent line. Oh yeah, it's just like in single variable calculus. Isn't that nice? This is one of the big reasons that people like partial derivatives. Again, very relatable to our old concept of derivative. So just to finish the thought though, partial with respect to y, yes, it's the slope of the tangent line. We do have to be a little bit more specific here. The tangent line to the graph of the function we're looking at. You got to make sure you're clear. This is only if we're talking about a graph, because we assumed that heavily in the analysis of the picture we just made. So slope of the tangent line to the graph. Now we have to further clarify though, because again, there's various different partials. We're looking here specifically at the partial with respect to y. So we get the slope in the y direction. So as I move in the y direction. Everybody on board? Okay. So now I'm going to leave this as an exercise for y'all, and this is a really healthy exercise. I hope you'll give it a shot. Think through, persuade yourself that the analogous statement about the x partial is also true. It's just some pictures to be drawn. You can borrow pretty heavily from the pictures I've got here. It's just going to kind of be pointed a different way because now we're taking the x partial, which means y is going to be a constant. So the plane's not going to go this way. The plane's going to go that way instead. And, everything's a little bit different. But morally very similar to what we just did. Again, very healthy exercise. I hope you'll take the time to persuade yourself that the x partial is the slope in the x direction. Everybody happy? Okay. All right. Okay, now all that was about graphs. And in single variable calculus, the only picture you have to worry about, again, not so. In multivariable calculus, we're going to have a bunch of different kinds of pictures. So let's start thinking through our other pictures and what do partial derivatives look like. Here's my next picture. Recall we talked about the literal picture of the function. I can just straight up draw the domain, right? I can just literally draw the target. And I can think of what the function is doing as taking points out of the domain and putting them into the target, like so. About as literal as I can get for drawing what the function is and what it's doing. In this context, what's a partial derivative? What does it look like? Is it a slope of a tangent line? Absolutely not. There's no curve of which to take a slope of a tangent line. This is not there, right? So, how would I interpret? Well, just keep in mind what a partial derivative does. Partial derivative is a single variable derivative. Derivatives in general, again, relate input changes to output changes, right? Old fact about derivatives. This is a statement about single variable derivatives because ultimately a partial derivative, very first thing we do when we're defining a partial derivative is say, I'm going to view this as a single variable function. And so this partial derivative is a relationship between input changes and output changes. However, again, got to keep in mind, this is a partial derivative. That means y is the only variable that's allowed to change. That means x and z are fixed. That means that I am stuck on that line that fixes x and z. Is everybody good? Okay, so now again, that looks different than the picture that we drew when we were talking about partial derivatives in the graph context. This is a different picture. Of course it looks different. Okay, so x and z are fixed. That means I'm only allowed to move in this one direction. And what does partial with respect to y then mean in this picture? Well, I guess here's my input change dy, and that's going to cause an output change. My function is going to change by, something like that, whatever. That's df. And so now, I can't combine this into a single geometric concept and say some really convenient word like slope, right? But I can say, the partial derivative tells you, what's the factor that you multiply by the green input change to get the blue output change? It's that relationship, right? And not as satisfying. But again, what's your alternative? If you think about your alternative here, if you say, phooey on this literal picture, I'll just look at the graph of this function. Oh, no, you won't. The graph of this function is a picture in 4 dimensions, and that's not on the table. It's out of the question. Right? So what we've got here is at least a way to make some sense out of a partial derivative in an option where this just doesn't work at all. This is a massive faceplant catastrophe. Doesn't work. Everybody okay? All right. Level sets. Now again, a totally different picture. Right? Here's a bunch of level sets that I've drawn here, just to kind of get the ball rolling, a bunch of level sets. And, again, the answer that the interpretation we're going to make of partial derivatives here is going to be, it's not super good. But it's important to have some sense, at least, for, vaguely what do partial derivatives mean. in these different contexts. So here we go. Let's think about partial derivative with respect to x. Partial derivative with respect to x says I'm going to move in the x direction. So from here I'll be going that way. Because y is constant. Right? So in fact, let me go ahead and y is constant, so y is not allowed to change. So I'm going in the x direction like this, and as I go in that direction, is the function changing really fast or not so fast? Or I mean, again, these level sets aren't labeled. I don't know what the vertical separation is between these lines. Is each one of those lines, 50 feet of elevation, or is each one of those lines 200 feet of elevation? Not indicated. So there's going to be a certain amount of a sloppiness here. But what I can say is that as I move in the x direction, let's see if I can do this. I'm going to have to zoom in so I don't have to fine motor control otherwise. Whatever is going on here is over a very short distance in the x direction that I gain, whatever altitude it is between those contour lines. That sounds pretty steep to me, right? I'm gaining, 100 feet over a very short little horizontal distance. That sounds steep. That means that the partial derivative in the x direction is large-ish. Again, relatively. Now, by contrast, let's think about what happens as I move in the y direction. If I take the partial derivative with respect to y, it's going to turn out that this is going to be, I'm going to claim small, because as we move in the y direction, and again, let's zoom back in so we can see better. As we move in the y direction, it takes me quite a bit more horizontal distance to gain the exact same amount of altitude, whatever it is, right? So relatively speaking, the y partial pretty clearly going to be smaller than the x partial. Everybody buy it? Now, this is a geometric interpretation. It's sloppy. It's not perfectly exactly a single thing that I can represent. But it's a geometric interpretation of sorts. And this is how you interpret partial derivatives in the context of level sets. And notice neither one of these is the slope of the tangent line. It's just not. Right? And if you misunderstand, if you conflate graphs and level sets and come on, they're all just pictures. Right? And if you just broad stroke interpret, partial derivatives, they're kind of like single variable derivatives, they're, slope of the tangent line. No, not at all. Not even close, right? The slope of this red line just is neither of these partial derivatives. Everybody happy? Okay. All right. Moving along. Okay, so I want to talk about something else that's going to be kind of a rip-off of an old single variable calculus idea, linear approximation. So I hope you all will recall, and look, the way you saw linear approximations in high school or wherever you took single variable calculus might have been a little different. My personal preferred point of view, a combination of reasons, is to think of a linear approximation as the unique first-degree polynomial that agrees with the function in value and derivative. So this is the unique first-degree polynomial that's mimicking the function as best as possible, both in terms of the value it has and the way it's changing. It's the best rip-off, the best approximation in some sense, but the best mimic, I think, is the best way to think about it, of what the function's doing at the given point. So now I claim that this is the formula that does it. And I hope this is a familiar formula. If you don't believe me that this does it, you can check at the given point, at this point A, where we're doing the approximation, at that point A, this function that I've written down has the same value as f, and it has the same derivative as f. It is a mimic of f at that point A. Is everybody on board? Okay. By the way, it's a healthy exercise. You want to make sure that you can do that. You're going to make sure that you can confirm this fact, and more to the point, you can confirm this fact. Right? It's just there's a little slight subtlety to it. It's not hard, but it is, a little slight subtlety. Okay. All right. So with this in mind, if you have a multivariable function of n input variables, I'm going to write down a function that agrees with f both in value and in derivatives. But wait a second, there's a bunch of different kind of derivatives. There's a bunch of partial derivatives. I need all. Again, I want L to be mimicking f, and so I want L to mimic f both in value and in all of the partial derivatives. Again, it turns out that, as long as there's nothing bad happens, there's some nasty functions out there that we're basically going to sweep under the rug in this class. But other than nastiness of that sort, here's the function that does it. This is the formula for L. This is called the linear approximation of f. And even notice that structurally it kind of looks like the single variable linear approximation. There's the value that f actually is at the given point. Now, of course, the given point up here is a point in R1, so it's just some number A, some point on the real number line. Over here, now, this is a point in Rn, so it's a vector, right? I mean, I'm going to treat it as a vector for notation, but it's actually a point. So again, keep in mind one-to-one correspondence and all that. But this point A is a multivariable, list of coordinates, not just a number. Okay, so it's got the same kind of first term, and then it doesn't have exactly the same kind of second term, but do notice that something kind of like that is there. And et cetera, and so ... and then something kind of like that here. You basically get one of these terms, a term that looks kind of like that, one for each of the input variables. You might call this the x1 term, et cetera, and then lastly, this is the xn term. Right, a bunch of different terms, but each one individually looks a lot like that. So not a huge shock that this might be how the formula works out. And again, a really healthy exercise. I hope everyone will spend the necessary 3 minutes, 5 minutes, and confirm that this function described there indeed not only has the same value as f at the point A, but it has the same x1 partial as f at the point A. And furthermore, the same x2 partial and the same x3 partial, and all the way out to and including the same xn partial at the point A. Very importantly, all at the point A. Yep.
What is the bar A?
Oh, yeah, that's just a notational thing. This right here is just a notational alternative to saying partial f with respect to xn of A. It's just. But the problem is that, I mean, if you look at how this was written here, then I would have an expression and then something in parentheses and then something else in parentheses, and it makes it look like you're multiplying. And so sometimes I prefer this bar notation to kind of avoid this potential confusion. Yeah. Is everybody okay with that? It's just notation. Yeah. And by the way, pretty standard. I didn't make it up. Okay. All right. Okay, so there you go. Here's our linear approximation. And gripe about this linear approximation, this ... business is a little unfortunate, right? And even if you're okay with that, it remains there's a lot of terms here. It goes almost all the way across the page. It's kind of clunky. it'd be nice to figure out how to streamline this notation. And so just for notational purposes, I'm going to first observe that all of this business looks like a dot product. That's just notation, just the way it lays out on the page. But I mean, I can see right here, for example, I've got all of the various coordinates of the vector x minus a. And then all of this stuff, those are the coordinates of, something else. We can write it down. These are the coordinates of this thing that I'm going to put a box around right here in blue. And just real quick, that thing, notice, dot with the x minus a vector is exactly, is exactly all of that great big clunky nonsense that I have up there. It's just much more compact to write it like this. I can take a bunch of terms and rewrite it as a dot product. Very convenient. It's just notational convenience, but nevertheless, it's kind of convenient. So the thing that makes this possible, this thing here that I have in blue, I'm going to give it a name and a notation for the moment just to allow me to use this notational convenience. So here we go. It's called the gradient. And we use this notation right here. It's kind of an upside down triangle. I know that's a weird looking notation, but it's just notation. And so this thing is the gradient of a function. Does that make sense to everybody? Okay. All right. Now that said, eventually we're going to find that this is much more than just notational convenience. But not yet, right? At the moment, it's just a notational convenience, and the other awesome facts about it will reveal themselves as surprises later. Okay. All right, so here we go. Here's our formula for doing a linear approximation. How would I write a linear approximation of this function at that point? Oh, just going to use my formula. And here we go. Let's see here. Apparently I'm going to need, first thing I'm going to do is compute the gradient. I know I'm going to need it. Here it is. The gradient. It's made up of all the various partial derivatives. So let's compute all the partial derivatives of f. Okay, so I got to take the x partial and the y partial. Yeah. Keep in mind when you're taking partials, as part of computing that gradient, when you're taking partials, you treat the other variables as constants, and so that's why you get these expressions here. Again, make sure you're good with that. Make sure you're comfortably proficient with computing partial derivatives. Okay. Now the formula that I need says I don't need the general gradient. I need the gradient evaluated at my point A. So I've got to take this 1, 2 and plug those values 1, 2 into these expressions, and that gives me then my actual, let's see here, let's see here, let me do it like this. So my gradient was that, but my gradient evaluated at the point A is going to be what I get when I plug in the point A, and that gives me 2, 4. Everybody okay? All right. So 2, 4. My formula has already, I've kind of done most of the work here in computing this linear approximation. I've got my gradient computed. Let's see, all I've got to do now is x minus a. Okay, well, x has coordinates x and y. A, of course, we already know, has coordinates 1, 2. So there's x minus a. And then I got to plug in and compute the actual value of this function at the point A. That, again, is just a little arithmetic. No big deal. Turns out to be 5. And there you go. There's your linear approximation. Just straight up plug and chug. Everybody happy? Okay. All right. Now, just a triviality of notation. You could take all of this and multiply it out and collect terms, etc., and rewrite it like this. If what you're doing with this linear approximation, if you're coding it into a computer and you're going to be computing it countless times, right? And for that purpose, you want your formula for your linear approximation to be as tight and efficient as possible, then I suppose this is nice. But we're not going to be coding anything in this class, right? That's somebody else's problems, the way I see it. So you could do this, but frankly, I don't see what the purpose is as far as Math 219 goes, right? So in Math 219, you're perfectly welcome to just leave it like this. In fact, I'd say you're encouraged to leave it like this because there's useful information in the way this is written. I can infer from what's written. I can see what the gradient is, and I can see that point x minus a right in there. It's just kind of useful to leave it in this form for our purposes. Is everybody okay with that? So good news, that's just saving you a step of algebra. Okay. All right. And you know what? We're out of time, so I'm going to draw the line right there. Actually, you know what? Let me just give you all a heads up. This next page, we are going to be skipping. And so in fact, I'm going to draw a line right here because all this stuff up here is Math 219 that is not Math 212 appropriate. So there's our line right there. Okay, see y'all later. Have a good one.